Hello everyone, welcome to another video. This is kind of branching out a little bit. It's not about STK exactly, but there is some STK in there. We're looking at a piece of code I wrote and have written a blog post about recently, which will come out at the same time, called mol-ellipsize. Basically, we want to calculate the molecular size, or the size of a molecule based on fitting an ellipsoid over the shape of that molecule. And if you do it over n conformers, which mol-ellipsize provides, then you get a picture of the flexibility or the size of this molecule as a function of its flexibility. It's automated, it's high throughput, and it has little human intervention, which means you can apply it to many thousands of molecules. And so this is what this code was for. I want to make this video quickly, so I'm not going to dive too deep into how the code looks and all that. There is a blog post that describes how it works. I just want to go through some examples, and unlike previous times where I've written the code out, I want to just go through this kind of plan here, looking at using mol-ellipsize, and I will have the code already written. I'll just run through the lines. So as per usual, we have import statements, so you can install mol-ellipsize through pip and import it. I like to import it as MES, but do as you please. We have some helper functions for visualizing molecules, and the code was originally written to handle RDKit molecules, and in particular I wanted to go from a SMILES string, so a string representation of a molecule graph, use RDKit to generate multiple conformers, and then calculate the ellipsoid that fits them. So standard RDKit code here to take SMILES and generate a molecule. There's a helper function in the utilities of mol-ellipsize for calculating conformers. And so you have RDKit mol, which is the RDKit molecule class, and conformers is the list of conformers that are available. And we're just running this over n conformers. We then input it into the mol-ellipsize molecule class, and it just takes the RDKit molecule and conformers. So we run that, and we can visualize the molecule. It's benzene, so it's flat and quite rigid, and we can see that there's 10 conformers, and these are their IDs. So the ellipsoids can be extracted from the molecule method called getEllipsoids. There's no default parameters. However, throughout the examples you can see these parameters for the box margin, which tells you the size of the grid to use, the spacing, which tells you the resolution of the grid, and then the scale of the van der Waals radii given here. And so these are just based off parameterization that I've done previously and mentioned in the blog post. What I will say is that RDKit actually provides a shape, a series of shape functions which take your molecule, places it on a grid, expands it to its kind of van der Waals cloud, so it considers the van der Waals radii of all the atoms, and then you can extract points on that grid that are within the van der Waals cloud of the molecule, and we use that as input to fit the ellipsoids to. So the ellipsoids class, which was taken from another GitHub repository, fits an ellipsoid to all of these shapes, and so this is the most costly part of the code because it depends on the resolution and size of the grid and the number of conformers, but it can be quite costly for larger molecules. It outputs ellipsoids as a dictionary, so the conformer ID is the key, and then you have the centroid, diameters and rotation matrices of the ellipsoid, the minimum volume ellipsoid that fits to that shape. We can extract those, and there's some helper functions in mol-ellipsize for plotting the diameters of those ellipsoids. So hopefully I can open that on the left, zoom out. You can see that benzene has two very similar large diameters, which makes sense. It's an oblate molecule, and then it has one thin dimension, and you can see that here. Similarly, for the molecule class, we provide inertial ratio calculators. Again, it's just a wrapper for RDKit code, And this is helpful for looking at the shape of a molecule, which again, if we open, you can see that benzene, as you expect, is oblate, and all of the conformers are oblate. They're all down here because it's not a flexible molecule, so the conformers are all going to be the same. And we also have helper functions which don't produce the prettiest of images, so I would recommend taking that code and modifying it to get really pretty images, but nonetheless you can visualize the ellipsoid by itself and visualize the ellipsoid surrounding the points on the grid that make up the shape of the molecule, shown in green. And so that's these functions here. Cool. Again, I'm not going into too much detail, but we can do the same thing for a flexible molecule, C6, linear C6 here, and doing the exact same code. You can see that we get out linear C6, it's good. And when we look at the, calculate the ellipsoids, get the diameters and the ratios, we can make those two plots, and hopefully once that's done I will be able to show you the figures. So the shape, as we expect, the molecules are more prolate than oblate in this case, and there's some deviation amongst the conformers, which again we would expect. And we can look at the size distribution. In this case, being oblate, you have two similar diameters kind of looking long way across the molecule, and then one long diameter shown here, but again there's some width to these distributions. So these are all kind of inbuilt into mol-ellipsize and make it easy, although you would obviously do the analysis you would be interested in. I promised some STK, and I just want to show that the method within STK for taking an STK molecule and converting it to an RDKit molecule works for input into mol-ellipsize. So you can build a linear polymer here, which we're doing. So we have two building blocks. Linear polymer, we're just increasing the number of repeat units from 1 to 3. And so what we're going to see when we run this, we get a mol-ellipsize molecule, look at only the first conformer because an STK molecule only has one conformer. We can run the get ellipsoids method on these molecules, and we can get the diameters. And if we print them, you can see that 2 of the diameters stay the same as you increase the length, but the third diameter increases again, as you would expect, as the length increases in this dimension. So this all makes sense. It's simple to use for any use case. The final thing I want to show is that you can apply mol-ellipsize to arbitrary coordinates as fake molecules, or you can make molecules however you want in RDKit. But you can also do them with just the coordinates, but I'll show the RDKit part first. So this is just an example code for taking a list of atomic numbers, bonds, and atom positions, and using the RDKit editable mol to add atoms, bonds, generate a conformer, and this generates just a molecule that looks like so. So it's effectively an 8-point sphere, and we can then input that molecule into mol-ellipsize and get this fake molecule makes a nice sphere with a centroid at this value near 0, as we expect, and diameter of about 4. The inertial ratios are near 1, so it's spherical, as again we would expect, but you can see that there's resolution issues. And this is because the grid is defined as well as it can be based on our resolution, and we can modify these parameters, so the box margin and the grid spacing, to change that. You'll also notice that even though the points are all at values of 1, the diameter is more than that, and that's because all of these atoms have van der Waals radii, which determine the shape of the molecule, not just the position of the atoms. However, we can forego that by just taking the same points and using the ellipsoid tool class directly and just calculating get min vol ellipse on those points. And you see now they give a nice sphere at 0, 0, 0 with radii 1, 1, 1. So it's an ellipsoid with radii 1, 1, 1, so it's a sphere. Just to highlight its usability again on these kind of arbitrary XYZ coordinates. We can take a pore mapper example from my previous video, which we can visualize here. So we have 4 pores, 2 of which are spheres of radii 0.1, and then 2 of which, so one is like this oval shape with one long axis. The other is quite spherical, although not a perfect sphere. Obviously, it's got some points jutting out. So we can run mol-ellipsize on those coordinates after reading in the XYZ coordinates like so. We can run the get min vol ellipse on those coordinates, and if we do so, it shouldn't take too long, but we see we have 2 that are basically spheres of 0.1, and we can show this in their plot. So the ellipse fits on the red points, which are the points of the pore. And then we have an example of an oval shape with one very long axis compared to the other 2, and then one of the more spherical cases. So that's a quick introduction of what mol-ellipsize can do. I do want to emphasize that there's a lot of different ways you can use it. The RDKit interface makes for a very nice and automated way for calculating the size of thousands of molecules, which is something I had done previously. Thank you for listening, and please let me know if there's any comments or issues. Thank you.